Hi everyone, welcome to CS350 Operating Systems. This is Karthik Gopalan. This lecture will cover the topic of CPU scheduling, or how different processes obtain control of the CPU resource. Let's begin by revisiting the concept of a process life cycle. We had covered this earlier when we talked about processes, so it's worth taking a look at the process life cycle again in order to understand what role a CPU scheduler plays. There are three primary states through which a process transitions: ready, running, and blocked. Ready state is when a process is ready to execute its instructions, but it does not yet have control of the CPU. In this case, the process just waits in a ready queue till a scheduler picks it up. So the transition from ready to running state is shown by transition 3, where the when a CPU scheduler picks up a process from the ready queue, the process is scheduled on the CPU. At this point, the process transitions to the running state. Next, when a process voluntarily gives up the CPU, it transitions from running to blocked state. This is shown by transition number 1. Finally, when a process receives the event that it has blocked upon, then it will transition back to ready queue. Occasionally, a process will be preempted in running state. The preemption operation is shown by transition number 2. So with this process life cycle in mind, now let's take a look at the operation of a CPU scheduler. We have also seen the CPU scheduler earlier when we discussed processes. Again, we have a queue of ready processes which are in the ready state, which means that they are about to execute new instructions, but they don't yet have control of the CPU. CPU scheduler is a piece of logic inside the operating system that decides who gets control of the CPU next. So the key job of a CPU scheduler is to go through the queue of ready processes and pick the most eligible process to execute. This process doesn't have to be the first process in the ready queue. The CPU scheduler can use any scheduling criteria to pick the most eligible process. A scheduling decision happens at several points during a process lifecycle. When a process switches from running to waiting state, in such case the process voluntarily gives up the CPU, and the CPU scheduler's logic would be invoked to pick the next process to execute on the CPU. Secondly, if a process switches from running to ready state, then it means that the process was preempted, and the CPU scheduling logic must again pick another process to execute on the CPU. Similarly, when a process switches from waiting to ready state, then at this point the CPU scheduler may again be invoked to switch control of the CPU to another process. Finally, when a process terminates or dies, then obviously the CPU has to be occupied again by another process. So in all these cases, a CPU scheduler can be invoked. Now, let's take a look at another important concept, that of a dispatcher. Oftentimes people confuse a scheduler and a dispatcher. A dispatcher is not the same as a scheduler. Scheduler is a piece of logic that decides which process goes on the CPU next. A dispatcher's job is to take the state of the process that has been picked by the CPU scheduler and to install it on the CPU. So a dispatcher's job is also known as context switching, which means that switching this control of the CPU from one process to another. Context switching involves installing the register state of a new process, which includes the program counter, stack pointer, general purpose registers, and so on. And then it also involves installing the memory state of the process. Where are the page tables of the process? What is the base register of the page table? These are some of the concepts we will visit when we cover memory management later in this course. So context switching obviously has an overhead. It is sometimes non-negligible overhead. If you perform context switching or dispatching too often, then the system can experience a significant slowdown. So dispatch latency or context switching latency refers to the amount of time it takes to switch the CPU from one process to another. This overhead is usually constant, but the frequency with which context switching happens can determine the overall overhead of context switching. Obviously, fewer the context switches, better the system performance. So you can take a look at the Linux CPU scheduling and dispatching code by browsing the Linux source code. If you go to the website shown on this slide, you would be able to browse down to a directory kernel/sched, and within that there's a file called core.c. Here there is a specific function called schedule that implements the CPU scheduling logic as well as dispatching logic. So there are three ways in which any code in the operating system can be invoked. Remember that operating system code is just a bunch of code that can be invoked in multiple ways. Operating system is not a process that begins at one point and terminates at another point. And unlike standard processes, operating system code just exists in the user memory, and then it can be invoked from various entry points. So how are the different ways in which operating systems code can be invoked? There are primarily three ways. A process can either invoke a system call, in which case you transition control of the CPU from a user level process into the operating system. There can be hardware interrupts that can invoke the operating system code. So whenever there's a hardware interrupt, the CPU stops doing whatever it's doing. It switches control into an interrupt service routine within the operating system, which then executes further operating system functions. Finally, whenever there are exceptions, then operating system code can be invoked. Exceptions mean things like whenever a process makes an error, for example, a floating point error or division by zero, or a null pointer access, or a segmentation violation. So in all of these cases, exceptions are raised by the hardware. And again, just like interrupts, there are exception handling code functions in the operating systems, and these exception handlers execute specific routines that handle the exception condition. So uh, for Linux 4.2 kernel, if you're looking at the x86 architecture, then you can find all the entry points into the operating system at the files that are listed here. Depending on whether it's a 32-bit or a 64-bit architecture, you will have to look at entry32.s or entry34.s files. Note that these are assembly files. The code listed in these files is in assembly code, but it's still readable. So it's if you just use a little bit of intuition, you will find that much of the code is readable. So it's not terribly complicated. So next, let's take a look at when exactly the CPU scheduler code executes. There are primarily two ways in which the CPU scheduler's code can be executed. First is if um, a timer interrupt fires, which means so every computer has a hardware that implements a timer functionality. So usually the timer can be programmed to interrupt the CPU at certain times. Most operating systems would program the timer to interrupt the CPU periodically. The period for interrupting the CPU can be, say, 1 millisecond or 10 milliseconds, It's really up to the operating system designers to program this functionality. For Linux, it so happens that you can change the frequency with which a timer interrupts the CPU by changing certain variables in the Linux source code. So there's a specific variable called HZ or Hertz, which you can search in the Linux source tree, and that determines how frequently the timer interrupt fires. So whenever the timer interrupt fires, the interrupt handler for the timer interrupt would check whether the CPU scheduler code needs to be uh, invoked, and at that point, if there is a need to invoke the CPU scheduler code, then the corresponding routine in core.c file would be invoked. So again, all these examples that I'm discussing are very Linux specific, but the generic mechanism would be the same across most operating systems. The other way in which CPU scheduler code is invoked is if a process voluntarily gives up the CPU. That is when a process transitions from running to blocked state. So in such a case, the operating system code um, would have logic to automatically invoke the CPU scheduling code. So at this point, I would encourage you to take a look at the CPU scheduler code, specifically the schedule function. If you click on the link that's listed in the slides, then it will automatically take you to the scheduling code in Linux. Again, it may look a little bit intimidating at the first shot, but the basic logic for CPU scheduler code is very easy to figure out. I will also discuss some of this in the class, so make sure you attend that discussion. So in general, the way CPU scheduling code would be invoked is there are various entry points in the operating system. Whether you invoke the scheduler code through a timer interrupt or um, when a process voluntarily gives up the CPU, there are entry points in specific files called entry32 or entry64.s, and these entry points check for certain conditions. They invoke the schedule function, and the schedule function has a piece of logic that determines the next process to be scheduled. And once the next process is picked, then towards the end of the schedule function, there's a dispatching code which performs context switching. And within the context switching, you can see that there are specific routines for switching the memory management context, and there are specific functions for switching the register and stack context. Again, we will discuss this in class, so make sure you attend that discussion. But this is not something you need to memorize, just this is for your information, so you have an easy time locating the code in the future. I had mentioned earlier that the process to be picked by the CPU scheduler does not have to be the first process in the ready queue. There are various scheduling criteria that a CPU scheduler can apply. So for example, one of the criteria could be to maximize the CPU utilization, that is to keep the CPU as busy as possible, which could mean that you want to have as few context switches as possible. There could be another CPU scheduling criteria, which is to maximize the number of processes that complete their execution per unit time. So in this case, you might want to execute the smallest jobs first before you execute longer jobs. There are other criteria such as turnaround time, which is the amount of time to execute a particular process from submission to termination. Waiting time, which is the amount of time that the process is waiting in the ready queue. Remember, note that waiting time can be a bit confusing. Uh, some people may confuse waiting time as the amount of time in the blocked state. That's not the case. Remember that here the process is ready to execute, but it doesn't get control of the CPU. So waiting time here refers to the amount of time that a process is waiting to get control of the CPU, amount of time it's waiting in the ready queue. Finally, there is response time. For interactive applications, it's very important that the applications respond quickly to users' input. So, for example, if you type something on on the keyboard, then you want your application to respond quickly to your keyboard input. So in such cases, the amount of time it takes from the time an input is submitted to the time the application first responds to the user. This is known as the response time. So the corresponding optimization criteria for each of these scheduling policies are given in the second column of the slide. So different types of systems have different scheduling criteria. Not all systems are the same. For example, a system that handles general purpose computers on your desktop may be different from a system on your mobile phone, or it may be different from a scheduling system in a flight avionics system, or from one managing a nuclear reactor. So so given the requirements of a system, the scheduling criteria could be different. Most systems have some sort of fairness policy, meaning that different processes should be able to fairly access the CPU resources. There are certain policy goals, like different systems may have different policy criterias. Um, you know, there may also be utilization criterias to keep most parts of the system busy. There are if you dig into specific systems, you can look at batch systems where these include systems such as high performance computing systems or mainframe systems, where it's very important to keep the CPU busy because these are very expensive systems. So you want to keep the hardware as busy as possible. So here the criteria could be throughput, turnaround time, CPU utilization, and so on. For interactive systems such as general purpose desktops or mobile phones, here you look at response time and proportionality, which is more subjective. Proportionality means whether you meet users' expectations, and sometimes meeting users' expectation can be a very subjective criteria. On the other hand, there are real-time systems where the criteria is that you have to finish certain tasks by some deadline. So the type of scheduling algorithms people use for real-time systems are completely different. So again, predictability is a big goal, meaning that if you want a certain task finished by a certain amount of time, you need to know how long all the tasks will take. So predictability and meeting deadlines are big criteria for real-time systems. So this is just to show that different types of systems have different scheduling goals, and you have to look at the specific system to decide what scheduling policy to use. Now let's take a look at the structure of a typical program as far as its behavior with respect to the CPU is concerned. All programs consist of alternating sequences of CPU execution and IO execution. So you'll have a bunch of instructions that execute on the CPU, and then the process gives up control of the CPU to perform some IO operations. And after some time, once the IO operation is complete, the process gets control of the CPU again. It executes a bunch of instructions again, and then it goes back to wait for IO operation again. So you have alternating uh, blocks of CPU burst and IO burst, then CPU burst and IO burst, and so on. So different processes can be characterized by how long are their CPU and IO bursts. So at one end of the spectrum, you may have processes that spend most of their time on the CPU. So in these processes have very long CPU bursts followed by very short IO bursts, then very long CPU bursts and very short IO bursts. So such processes are known as CPU bound processes because they spend a large portion of their life cycle executing on the CPU. At the other end of the spectrum, you have processes that have very short CPU bursts and very long IO bursts. So they may spend little bit amount of time performing a small amount of computation and then wait for a long time for some IO operation. Such processes are called IO bound processes. CPU bound processes and IO bound processes, these are just names that we give to the two ends of the spectrum. Different processes can be anywhere between these two ends of the spectrum. Examples of CPU bound processes could be uh, say high performance computing processes where you're say doing a very large numerical computation, but occasionally your process may do some input output. At the other end of the spectrum, you may have processes that are interactive in nature that wait for a long time for user input and then they may perform a small amount of computation. So the example of a command line shell that you are doing in your assignments, that's an example of an IO bound process because a shell waits for a user's input for most of the time. When the user types a command, it executes the command and then goes back waiting for the input. So an example of a process that may lie somewhere in between would be say a video game where you have user input that is a key driver of the video game, but then the processing of the video and the graphics itself can take up a significant amount of CPU computation. So the way we classify CPU bound process or IO bound process, this is not a strict classification. Process can also lie somewhere in between. The reason we are discussing all this is because the length of the CPU burst for a process plays a very critical role in the CPU scheduling decision. Often the CPU scheduling algorithm would want to know how long will be the next CPU burst for a process. And depending on the length of the next CPU burst, the CPU scheduling algorithm may pick the most eligible process to be scheduled. So now let's take a look at some CPU scheduling algorithms. The simplest CPU scheduling algorithm is called FirstCome FirstServe scheduling. As the name suggests, whichever process arrives in the ready queue first gets to go first. It doesn't matter how long the process will take to execute on the CPU. As long as the process comes first, it gets to execute first. So in this example, we have three processes, P1, P2, and P3. P1 takes 24 units of time. P2 takes 3 units of time on the CPU, and P3 has a CPU burst of 3 units. So, uh, so the figure shown in this slide uh, shows the execution schedule. So obviously P1 executes for the first 24 units of the time, then P2 executes from 24 to 27 time units, and then P3 executes from 27 to 30. Now, if you look at how long different processes are waiting in the ready queue, we define a metric called average wait time, which basically measures how long a process is waiting in the ready queue. It means that the process is ready to execute, but it's not getting control of the CPU. Obviously, if you have a longer average wait time, then it means that the processes are not as responsive to the users. This would be a bad thing for, say, interactive processes. So if you look at the average wait time metric, then it's very easy to compute this. Uh, Process P1 waits for 0 amount of time before it gets control of the CPU because it came first. Process P2 has to wait for 24 time units. In this case, we are assuming that P1, P2, and P3 arrive very close to each other, but in the order P1, P2, and P3. So P2 waits for 24 time units and P3 waits for 27 time units before it gets control of CPU. And if you compute the average wait time, then the average wait time comes to 17. As we go through other scheduling algorithms, we will see how this average wait time is affected by the scheduling criteria. All right. Now, let's take a look at the same first come first serve scheduling algorithm, but with a different arrival order. In this case, we say that process P2 arrives first, then P3 arrives, and then P1 arrives. So same set of processes, same CPU burst times, but just a different arrival order. So in this example, process P2 waits for 0 time units, P3 waits for 3 time units, and now P1 waits for 6 time units. So the average wait time is 6 plus 0 plus 3 divided by 3, which is 3 time units. So on the average, each process waited for about 3 time units, right? So this is much better than the previous case where the average waiting time was 17 time units. So this is known as the convoy effect. What this means is short processes, if they are stuck behind long processes, then they will have to wait longer, and it affects the average wait time. So this also, keep this example in mind as we go further for the next scheduling algorithm, because it also leads to an intuition for how to reduce the average wait time. If response time for an application is important, then one way to reduce the response time is by reducing the average wait time. And these two examples of first come first serve scheduling give us an intuition that if you schedule smaller jobs first, or smaller CPU burst first, then the average wait time would be smaller. So that's precisely what the next scheduling algorithm does. So its name is ShortageJobFirst scheduling. As the name suggests, you would take a bunch of processes, and then the next process to be scheduled on the CPU would be the process which has the shortest CPU burst time. Now, so we are looking at the ready queue of several processes. We examine the next CPU burst time for each process, and then we pick the one that has the smallest CPU burst time. Again, this has two variants, preemptive and non-preemptive. I would discuss the specific behavior of preemptive and non-preemptive variants when we look at the examples. So there is also a claim here that shortest job first is optimal. What this means is that there is no other scheduling algorithm that can give you a shorter average wait time than shortest job first. Now this is a pretty strong claim. We are saying that you can come up with any scheduling algorithm that you can think of that has not yet been invented, and shortest job first will beat your algorithm in terms of average wait time. It will do at least as good as your algorithm or better in terms of average wait time. So we will look at how to prove this in a little bit from now, but keep this in mind as we go forward. All right. Now let's take a look at the first example, which shows non-preemptive shortest job first. So here you have four processes, P1, P2, P3, and P4. P1 arrives in the ready queue at time 0. P2 arrives in the ready queue at time 2. P3 arrives at time 4, and P4 arrives at time 5. The corresponding CPU bursts are also given. Note that P1 has the longest CPU burst of 7 time units, and P3 has the shortest CPU burst of 1 time unit. Now at time 0, we have only one process in the ready queue, which is P1. So P1 gets to go first. Now, because this is a non-preemptive version of shortest job first, it means that once we allow a process to start executing on the CPU, we will not preempt it. The CPU scheduler will allow the process to execute till the process voluntarily gives up the CPU. What this means is that process P1 will get to execute for full 7 time units before it is forced to give up the CPU. Next, at time 7, the CPU scheduler will go back and look at the ready queue, it finds that processes P2, P3 and P4 are waiting in the ready queue. It will look at the CPU burst time for P2, P3 and P4. Of the three processes, P1 has the shortest CPU burst time. So process P3 gets picked and gets to execute at time 7. Once P3 finishes at time 8, then the CPU scheduler again looks at the ready queue. It finds that P2 and P4 are waiting, and since P2 and P4 have the same CPU burst time, it doesn't matter which one you pick. So in this case, we happen to pick P2, maybe because it arrived earlier than P4. So next P2 executes from time 8 to 12, and then P4 gets to execute finally from time 12 to 16. So this is a non-preemptive version, meaning that once a process starts executing on the CPU, we do not preempt it, even if a shorter job arrives in the ready queue. So if we do this, then the average waiting time in this case comes to 4 time units. You can compute how long each process waited in the ready queue before getting getting control of the CPU, and take an average of that. So note that to compute the wait time for a process, you have to also consider its arrival time. For example, process P3 arrived at time unit 4 and it received service at time unit 7. So P3 waited for 3 time units, which is 7 minus 4. Okay, and similarly for other processes. So this is non-preemptive shortage job first. And then there is a preemptive version of this that we will consider next. The preemptive shortest job first is a slight variant of the non-preemptive version. So in this case, when a process is executing on the CPU and another process arrives in the ready queue, which has a smaller CPU burst than the remaining time for the current process, then the newly arrived process would be scheduled instead of the current process. So there is a preemption of the current process that's involved if a shorter job arrives in the ready queue. So let's take a look at the same example as before. In this case, P1 starts running at time 0 with a CPU burst of 7 time units. When P2 arrives at time 2 time units, at that time P1 still has 5 units of CPU execution still remaining. So the CPU scheduler will compare P2 and P1. It finds that P2 has a smaller CPU burst of 4 time units, whereas P1 has 5 time units remaining. So the CPU scheduler allows P2 to execute and preempts P1 from the CPU. So there is a preemption going on at time unit 2. So again at time unit 4, P3 arrives, and this is again a scheduling point. So CPU scheduler will compare 3 processes, P1, P2 and P3. P1 has 5 time units remaining, P2 has 2 time units remaining at time 4, and P3 by contrast has only 1 time unit of CPU burst. So P2 gets preempted and P3 is scheduled on the CPU. After this, at time unit 5, P3 finishes execution, but at the same time P4 also arrives. So the CPU scheduler then compares the remaining CPU burst times of processes P1, P2 and P4. P2 still has the lowest CPU burst time, so P2 continues to execute till time unit 7, at which point the P4 and P1 are compared. P4 has a smaller CPU burst time, which is 4 time units, compared to P1, which still has 5 time units remaining. So P4 goes first, and at 11 time units, P4 completes execution, and then P1 gets its turn again, and finally P1 finishes execution at time unit 16. So As you can see that P1 got a chance to execute at time unit 0, but once it was preempted, it could not get control of the CPU back till time unit 11. So as you can see, if it so happened that smaller jobs kept arriving ahead of process P1, then P1 could have been delayed indefinitely. This can also lead to a situation called starvation, where a process does not get scheduled for a long time because more higher priority processes keep arriving ahead of that process. So we will discuss more about starvation when we talk about a specific category of scheduling called priority scheduling. So, but here the point to note is that preemptive scheduling has a smaller average wait time than the non-preemptive version. In the non-preemptive version, we had an average wait time of 4 time units, whereas in the preemptive version, we have an average wait time of 3 time units, which is slightly better. And the reason we were able to achieve that is by moving shorter jobs ahead with the help of preemption. Now let's take a look at our claim earlier on that shortest job first is optimal as far as average wait time is concerned. What that meant was that shortest job first gives you the lowest average wait time compared to any algorithm you can ever devise. Now that's a pretty strong claim, and you can actually formally prove that by constructing a contradictory example. So this slide gives you an informal proof, informal outline of a proof. The intuition behind the proof is to take a schedule for processes that doesn't follow the shortest job first order, and to claim that this particular schedule is better than shortest job first as far as average wait time is concerned, and then to find a contradiction where switching the order of a couple of processes gives you a better average wait time. So let's say you have n processes, and let's say you have an algorithm X, a scheduling algorithm X, that gives you a better average wait time than shortest job first. It means that since X is not the same as shortest job first, it means that there are at least two processes in the schedule P1 and P2 such that P1 executes before P2 and the CPU burst time for P1 is longer than P2. Remember, if this was shortest job first, then P2 would execute before P1. Since it's not shortest job first, P1 executes before P2 does, right? So, and the other claim we have is that algorithm X gives you a lower average wait time, right? So which means that the schedule derived from algorithm X gives you a smaller average wait time than shortest job first. Now, if this were true, then we can fiddle around with the schedule to see whether we can um, get a better average wait time than what X gives you. So let's just take these two processes P1 and P2 and swap their positions in the schedule. Remember, P1 is a longer CPU burst and P2 has a smaller CPU burst. If you swap them in the schedule and recompute the average wait time, you would find that suddenly you have a smaller average wait time than what you originally had with algorithm X. So now you have another algorithm which is doing better than X. Okay. Now you can do this process repeatedly. You can find any two processes, any pair of processes where the first process in the schedule has a longer CPU burst than the other process in the schedule and swap their positions. And every time you swap the position, you will find that the average wait time is reduced. And if you keep doing this till all the processes are sorted by the order in the increasing order of their burst times, CPU burst times. So the final sorted schedule will be the same as shortest job first, and this final sorted schedule will have the lowest average wait time. So we started from an algorithm X which we claimed had a better average wait time than shortest job first, and then we just by swapping the position of pairs of processes, we arrived at the same schedule as shortest job first, which had the a lower average wait time than algorithm X. So note that we did not make any assumptions about what type of algorithm it is. It's just that we only claim that X is different from shortest job first. So that pretty much covers every other algorithm other than shortest job first. So this is a proof by contradiction, which basically proves that there is no algorithm X which is different from shortest job first and which can give you a smaller average wait time. Every CPU scheduling algorithm we have discussed so far relies on knowing the length of the next CPU burst for each process. Now this is a very important piece of information, but it's also a big assumption that we are making. For example, we are assuming that once a process starts running on the CPU, we can accurately predict how long it's going to execute. Now, for most processes for most types of code that people write, it is extremely hard to predict the next CPU burst. The next CPU burst can be affected by a number of different factors, which not just the speed of the CPU, but also the architecture of the CPU, whether there is a hyperthreading uh, or other types of parallelism in the execution hardware. So accurately estimating the CPU burst time for a process is a notoriously hard task. A common approach for predicting the next CPU burst time for a process is called exponential averaging. Now, this is a very simple approach to predict the future CPU bursts. So, if you take the past execution history or the CPU bursts of a process as a sequence of values, then what exponential averaging does is it predicts the next value in the sequence based on a certain combination of previous CPU bursts. So in this formula shown in the slide, we have several terms. One is Tn, which represents the actual length of the nth CPU burst in the sequence. Another term is tau n, which is the predicted value of the nth CPU burst. And then there is a factor alpha, which can vary between 0 and 1. Now we combine these three terms together to derive a prediction formula. So the formula states that tau n plus 1, which is the predicted CPU burst of the n plus 1th CPU burst, is alpha times Tn plus 1 minus alpha times tau n. What this means is that you multiply the actual CPU burst Tn by the factor alpha, and then you take the predicted value of the nth CPU burst tau n, multiply that by 1 minus alpha, and add them up, and that gives you the predicted CPU burst for the next round. Now what we are trying to do in this formula intuitively is to somehow combine the actual execution times with previous predicted values, and by varying the factor alpha between 0 and 1, you can get different sorts of behaviors. So let's take a look at an example of how this formula might behave. So in this example, we have a process that changes its CPU execution burst as time goes on, and at every time unit, we are trying to predict what will be the next CPU execution burst. So Ti represents the actual CPU execution burst, represented by the black line, and tau I represents the predicted CPU burst value. Initially, we start with some predicted CPU burst value, say 10, and it turns out that the process executes for only 6 time units. So next time we refine our prediction by lowering the prediction values. Exponential averaging may give you a predicted value of 8, whereas in reality the process may execute for say only 4 time units. So you reduce it further and further, um, till maybe say time unit 4, where suddenly the process takes 12 time units of time. So at this point, the prediction value has to increase, and you see that the predicted value predicted by exponential averaging would gradually increase till it catches up with the actual execution CPU burst times for the process. So the idea behind exponential averaging is not to have sudden jumps in the predicted value, but to gradually catch up with the actual predicted value. If a program shows consistent CPU burst over a long period of time, then exponential averaging would approach that actual stable CPU burst times. If on the other hand a program shows unpredictable CPU bursts, then no prediction algorithm is um, going to give you accurate prediction. So uh, just to get a better understanding of how exponential averaging behaves, it is instructive to consider some boundary cases. So there's the exponential averaging formula again. Tau n plus 1, which is the next CPU burst, is equal to alpha times Tn, or alpha times the actual value of the previous CPU burst, plus 1 minus alpha times tau n, or 1 minus alpha times the predicted value of the previous CPU burst. So if suppose that alpha was 0, okay, which means that the first term in the addition is irrelevant. Okay, so the formula reduces to tau n plus 1 equals tau n. What this means is the actual CPU burst history doesn't count. Whatever prediction value you start with at tau 0 stays the same for every subsequent CPU prediction. So we are basically ignoring the actual CPU burst and sticking to a fixed CPU burst that was selected at the very beginning, right? So this is one extreme where we set alpha equal to 0. At the other extreme, we could set alpha equal to 1, in which case the only term that would matter is alpha times Tn, the first term, and the second term would be completely irrelevant. So in this case, the formula boils down to tau n plus 1 equal to Tn. What that means is that only the value of the last CPU burst matters. Only the actual value of the last CPU burst matters. Any other predicted values in the past have no relevance. So here we would closely track the actual CPU burst from the previous round. So between these two extremes, of course, neither do we want to stick to the initial guess, nor do we want to rapidly change our prediction as the program's behavior changes. So what we usually want is a more gradual uh, change in the predicted value. That's why people may select some alpha value between 0 and 1, which gives them a reasonable stability in terms of the prediction. Uh, so so there's further analysis in the slide where we expand the formula for tau n plus 1. Remember that this exponential averaging formula is sort of a recursive formula, right? Where tau n plus 1 depends on the value of tau n, and value of tau n depends on the value of tau n minus 1, and so on. So you can expand that formula, and if you do that, you would see that that the predicted value is actually kind of a series of combination of values of tn minus 1, tn minus 2, and so on, all the way to your initial prediction tau 0. So what and if you pick a value of alpha, you'll see that subsequent values in the history have lower and lower significance or contribution to the value of tau n plus 1. So this is just another way of understanding what we are doing with exponential averaging. This is a very generic way of predicting the next value in a sequence, and it just so happens that we can apply it to CPU scheduling. Okay. There are of course other ways that people can use. Exponential averaging is not the only way to predict CPU burst times, and different operating systems may use different variations of burst prediction algorithms. So this is just to give you a sense of one specific technique for predicting the next CPU burst, which happens to be a fairly good and generic technique. Next, let's take a look at another common scheduling algorithm called round-robin scheduling. So the goal of round-robin scheduling is to give a more predictable response time for processes. Now, different processes can have different CPU burst times, but the goal of round-robin is to divide up the CPU control in equal sized time units. So if you have say 3 processes waiting to get control of the CPU, then process 1 will get a fixed amount of CPU time, then process 2, then process 3, and then you'll go back to process 1, and then to process 2 and process 3, and so on. That's why it's called round robin. So as the name suggests, there is a time quantum involved for that is where each process gets to execute for a fixed CPU burst time or time quantum. Usually the time quantum is in the order of tens of milliseconds. So in Linux, for example, 100 milliseconds is a standard time quantum that's allocated to a process. So after after the time quantum has elapsed, the currently executing process would be preempted, and then the next process in the queue would be scheduled for the fixed time quantum. Of course, the process can give up control of the CPU before its time quantum expires. So in which case the scheduler will move on to the next process. Now, if there are n processes that you are waiting in the ready queue and you have a time quantum of q time units, then each process would get 1 by nth of the CPU time, and each process would get to execute for a maximum of q time units at a time. So what that means is that no process would wait for more than n minus 1 times q time units. Now this gives some predictability in terms of how long your process would have to wait before it gets control of the CPU. So if response time is an important metric, you can adjust the value of q to give you the desired response time. Of course, q is a very important factor. The time quantum q is very important. If you have a very large time quantum, then the round robin algorithm will approximate the first in first out algorithm. This is because most processes would rarely get preempted. They would likely give up control of the CPU before they get to be preempted. If the time quantum q is very small, then you get better response time, right? That formula we saw in the previous bullet, n minus 1 times q, it will be smaller if q is small. So response times would be smaller, but on the other hand, you would be doing a lot of context switching. There'll be a lot of preemption and a lot of context switching. So the context switching overhead would be very large. See, context switching is not without a cost. So most scheduling algorithms have to find a balance between large response time versus too much context switching. Here's an example of round robin. You have 4 processes P1, P2, P3, P4 with different CPU burst times, and the figure shows you the Gantt chart, which shows how the CPU control switches. So you switch between P1, P2, P3, and P4 for a time quantum of 20 time units, and then back to P1, then P3 and P4, because in the second round P2 has finished execution, and then the third round is again between P1, P3, and the fourth round is for P3 alone. So round robin usually has a higher average wait time than shortest job first, but it also has a better response time, and it doesn't have starvation. Remember, we talked about starvation earlier, where a process could be indefinitely delayed in shortest job first because smaller processes keep arriving ahead of the longer process. So with round robin, it guarantees that there would be no starvation. A process would constantly keep making progress till it completes. We can look at the relationship between time quantum and context switching time again in the case of round robin. So in the first case shown here, we have a time quantum of 12, and if a process has a CPU burst of 10 time units, then there are no context switches involved in the first case. If the time quantum is 6 time units, then you have one context switch. If the time quantum is 1 time unit, then you will have 9 context switches. So smaller the time quantum, more the number of context switches, but you also have a better response time. Next, we look at a class of scheduling algorithms called priority scheduling. Almost all the scheduling algorithms that we have seen so far, except maybe round robin, falls under the category of priority scheduling. Within priority scheduling, there are two subcategories: static priority and dynamic priority scheduling. So the specific category we are discussing is static priority scheduling. So in static priority scheduling, as the name suggests, different processes are assigned different priorities, usually fixed priorities. So processes that have a higher priority get to execute on the CPU first. Processes that have a lower priority have to wait till the higher priority processes have completed execution. So again, just as with shortest job first, we have two types of priority scheduling: preemptive and non-preemptive. Under a non-preemptive priority scheduling, if a process is scheduled on the CPU, and let's say a higher priority process arrives in the ready queue, then the currently executing process would be allowed to complete its CPU burst, and then only the high priority process would get to execute. Under a preemptive scheduling policy, if a higher priority process arrives, then the lower priority process on the CPU would be preempted, and it would have to make way for the higher priority process. So shortest job first is a type of priority scheduling algorithm where the priority is determined by the predicted value of the next CPU burst. So in that sense, shortest job first is a dynamic priority scheduling algorithm where the priority depends on what will be the next CPU burst predicted for a process. So again, this is a general problem with priority scheduling algorithms, that you can have starvation. Some low priority processes may never get to execute. For example, in this case, let's say in the figure shown here, there's a process at priority 2. But if you have a lot of processes that keep arriving at priority 3 and 4, then the priority 2 process will never get to execute. So normally a solution to starvation is called aging. Aging means that if a process spends too much time at a lower priority, then after a certain amount of time you can bump up the priority of a process. So the longer a process waits at a lower priority, the more the likelihood that it will be bumped up to a higher priority. So soon enough, the process gains sufficient priority to get control of the CPU. So aging is a pretty standard technique. It's used in most common operating systems to make sure that there is no starvation. There is a related scheduling algorithm, which is how most commodity operating systems implement their scheduling. This is known as multi-level feedback queue. Just as with priority scheduling, you have multiple queues or multiple levels, and each of these levels have a different scheduling policy. So, um, so in this example shown here, you have three queues. Q0 implements a round-robin scheduling algorithm with a time quantum of 8. Q1 implements again round-robin scheduling with a time quantum of 16. And Q2 implements first come first serve algorithm. If you recall our previous discussion, first come first serve is basically the same as round robin except with a time quantum that's infinite. So we have successively larger time quantums as we go down the priority order. So the way multi-level feedback queue works is that, as the name suggests, there's a feedback involved. The multi-level feedback queue is defined by the number of queues, the scheduling algorithm for each queue, and in addition, there's a feedback mechanism, which is the way you determine whether to upgrade or demote a process in the priority order. So Q0 here has the highest priority and Q2 has the lowest priority. But the feedback mechanism allows a process to move up or down the priority order. So what is this feedback mechanism we're talking about? In this example, we want to give higher priority to interactive jobs or IO bound jobs, and we want to give lower priority to CPU bound jobs. So initially when a process starts, it starts in Q0 with a time quantum of 8. If, let's say, the process executes for 8 time quantums and doesn't finish, at that point the CPU scheduler can decide that, okay, maybe this process needs more CPU burst time, so I'm going to downgrade the priority of the process to Q1, where the time quantum is 16 time units. And let's say the process executes in priority Q1, but it still doesn't finish in 16 time units. So at this point, the process can be downgraded further to the last priority, which is first come first serve, and there it can execute for as long as it wants, but then it would execute as the lowest priority process in the lowest priority queue of the system. So processes that finish quickly within 8 time units have the highest priority. Processes that finish within 16 time units have the next higher priority, and processes that take longer than 16 time units have the lowest priority in the system. So this is just one example of a multi-level feedback queue. Of course, you can have other types of scheduling algorithm for each level, some other feedback mechanism for processes to move back and forth between these queues. So 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 this is just one example, and you can construct various types of multi-level feedback queue by varying the number of queues, varying the scheduling algorithm, and by varying the feedback mechanism. Finally, we will talk about real-time scheduling. Again, real-time scheduling is characterized by systems where processes have to finish by certain deadline. When would such a thing happen? For example, you may have, let's say, an industrial control system where certain tasks have to finish by certain time before the next task takes over. So here there are deadlines associated with each task. You can categorize real-time systems as hard real-time systems, soft real-time systems. Hard real-time systems are those where the deadlines have to be met. If you don't meet the deadline, then something bad may happen. For example, if you, let's say in a nuclear reactor, if you don't, you know, turn on the cooling by a certain amount of time, then maybe the nuclear reactor would melt, right? So here in hard real-time systems, predictability is very important. It means that you need to know exactly how long each task will take. You need to guarantee that each task with a deadline finishes before its deadline. Uh, on the other hand, you have other types of real-time systems such as soft real-time systems. Here it's desirable to meet certain deadline, but it's not critical. For example, let's say you are in a video conference with some participants, and generally you want to see 33 frames of video per second, and you want to hear audio at a certain sampling rate. If you meet the deadline, you get great video conferencing experience. But if you don't meet the deadline, then all that happens is that the video conferencing quality is poor. Maybe some frames are skipped, maybe you can't hear their voice properly, but overall you can still somehow manage. Nobody dies, nothing bad happens. So these are soft real-time systems where meeting the deadline would be nice, but even if you miss the deadline, the system can still continue to operate. So there are different types of real-time scheduling algorithms for hard real-time and soft real-time scheduling systems. There's also a notion of a schedulability criteria. What this means is that you're given a certain set of processes or tasks, and you're given their CPU burst times, and given all these criteria, can you guarantee that the deadline for each process can be met, whether a given set of processes are schedulable to meet their deadlines? Now, there is a whole theory in real-time scheduling behind under what conditions certain processes are schedulable, under what conditions they are not schedulable. So that would be a course by itself. So we are not going to get into the details of all that. In general, it's very straightforward to derive a very simple rule uh, for determining whether a set of tasks is not schedulable. You can compute the CPU utilization of all the processes. That is the CPU burst time divided by the periodicity of each task, how often each process repeats itself. If the sum of the CPU utilizations for all the tasks is less than equal to 1, then possibly the set of tasks are schedulable. If it is greater than 1, then there is no possible schedule that will satisfy all the deadlines. Um, there is also the notion of fair scheduling. Now, fair scheduling sounds like a really nice word, but there are very formal definitions of fairness in the scheduling literature. Notion of fairness doesn't mean that each process should get equal share of the CPU. That's what we would think intuitively. Fairness means everybody gets equal share. In CPU scheduling or in any scheduling literature, fairness has a more formal definition. Let's say you have n processes in the system. You can assign them different weights or different degrees of importance. So you can assign each process a weight Wi. Now, processes that have more weight get more share of the CPU. Processes that have less weight get less share of the CPU. Fairness in this case means that different processes get shares of the CPU in proportion to their weights. So if you have a process Pi and a process Pj, and their weights are Wi and Wj, then the amount of CPU time received by process Pi divided by the amount of CPU time received by process Pj should be equal to Wi over Wj. Now, so this ratio has to be maintained across all processes. So again, there is a large literature on how you can construct fair schedulers. Um, when you construct fair schedulers, you have to not only decide um, how to divide up the weights, how to divide up the CPU time according to weights, but also what do you do with extra resources, extra CPU time. If some process doesn't use up its CPU time, then that spare CPU time gets divided up among other processes. Again, that division of the spare CPU time has to be done according to the weights assigned to the process. Um, Finally, there is the notion of work conserving versus non-work conserving schedulers. I will cover this briefly just so you know what these terms mean. Work conserving means that the scheduler doesn't allow the CPU to remain idle at any time. If you have a process waiting in the ready queue, then some or the other process will be scheduled on the CPU. It means that the CPU is always kept busy. Now, it seems like an intuitive thing, right? I mean, if you have tasks to be done, if there are tasks waiting in the ready queue, why would you not schedule them, right? Well, it turns out that in some situations, it's desirable to keep the CPU idle. So in these type of schedulers are known as non-work conserving schedulers, where the schedulers purposely keep the CPU idle even though there is work to do. And oftentimes these uh, type of non-work conserving schedulers show up in real-time systems where you don't want to start a task too early uh, because then it would finish too early and you don't want it to finish too early. So sometimes introducing intentional gaps in the schedule is beneficial to the whole system. So in those cases, you're intentionally wasting CPU resource in order to meet some system goals. So, so that's what we mean by work conserving and non-work conserving. In work conserving, if there's work to do, then you keep the CPU busy. In non-work conserving, in some situations, you might keep the CPU idle even though there's work to do. So this gives you a general idea about CPU scheduling, various algorithms for CPU scheduling, and various terminologies that we have that relate to CPU scheduling. Terminologies such as exponential averaging, starvation, optimality of shortest job first, um, work conserving versus non-work conserving, real-time systems, and so forth. So with this, we would end the discussion of CPU scheduling.